Hey, it's Rez. All right, so this session is going to look at winds and how winds form and sort of global wind patterns. This is something that we will have completely gone over in class together, but I like to have this so that in case you needed to rehear it, you can. So to start, a couple things that don't mind that little direction. A couple things that we have to keep in mind with air. Okay, it's four major properties: density, water vapor, adiabatic heating and cooling, and latent heat release. Now, of those, we're going to spend the most time talking about really one through three. Four is going to come up briefly, so just bear with me on that one. So, in class, we saw the video of convection currents, right? And one of the really important things to know here is that warm air is lower density. Again, those molecules are moving around faster. It means they're a little more spread out, less dense. Less dense things are going to rise, right? So, warm, low density air is going to rise. Cooler air, again, they're moving less, they're kind of more condensed. It's a higher density, is going to sink. So that's what sets up that convection current. When in doubt, come back to that fact that warm air is lower density and it's going to rise, right? These are also going to come into play when we start talking about ocean currents because air and water are both considered fluids for our intents and purposes. So we get that. The other thing to note is that warmer air has a higher capacity for water vapor, right? It can hold more water in it. That's why in the summertime, we get much more humid days. We get a higher dew point. Cooler air has a much lower saturation point, so it cannot hold as much water. And that's going to come into play when we start looking at what causes rain. All right, so briefly to mention latent heat release, the idea with that is that as water vapor in the atmosphere condenses into liquid, that releases energy. And that energy warms the air around it, which rises. And that warm air rising, again, kind of powers things like hurricanes. So it's more of a weather thing we won't deal with too much, but just be aware that it exists. Now, adiabatic cooling is important. So if you think about this, again, logically, all of this makes sense. We have warm, humid air that's going to rise because it's less dense, right? But as it rises up in the atmosphere, it also starts to cool. Okay. There's less air pressure at higher altitudes. So, with that, it starts to expand. All right. As it expands, it's using energy. The molecules are starting to slow and that temperature is decreasing. So, we've got warm air rising, cooling, and expanding. That's the idea of adiabatic cooling. That's how air cools as it rises. Okay. Adiabatic heating is kind of the opposite. That cool air, again, remember, cold is more dense. Eventually, it's going to start to sink back down to the earth. As it sinks back down, it's getting more pressure and the temperature is actually going to rise. So, air as it's coming down is actually warming, and as it's going up is cooling. Okay, now with that part in class, we're going to skip that. But important point to note is always remember that air is going to move from high pressure to low pressure. Logically, that should make sense, right? If I have a balloon that is filled with air, right, there's a lot of it's higher pressure inside that balloon. When I release it, the air is going to move from high pressure out into the world where it's lower pressure. Logically, that makes sense. Keep that in mind because this gets tricky. All right, so we're going to take into account all those air properties that we just talked about. So I'm over on the right here, right? Warm air rises. It holds more moisture than cold air. But as air expands, it cools. Okay, we know that cold air can't hold as much water vapor. And after it cools, it's going to start to sink. So let's translate that into this stuff with what's going on the Earth. So imagine the equator. We just talked about solar insolation is really high on the equator, right? We get a lot more direct sunlight there. That means the air is warming. Well, warm air, less dense, it is going to rise up, right? I feel like that's a song. I won't start singing though. So it's going to rise. As it rises, it's cooling, right? It's also expanding. As it cools, a lot of that water vapor is going to start to condense into rain. So we get rain. So the tropics, right, where we have more direct sunlight, where we have that rising warm air, tends to get more precipitation in those areas. As that air continues to cool, now it's also losing moisture. It's also continuing to rise. It's also expanding. It's eventually going to, you see those kind of kick out. It's eventually going to start to spread out and sink back down. Now on Earth, that air sinks back down right around the 30-degree latitudes, north and south. If you look on a map at the 30-degree north and south latitudes, that's cool, dry air that's coming down, right? we typically have deserts form there. We have really dry, arid areas. Okay. Now, the other thing to think about is think about where there's high and low pressure. If in our tropics, I've got a lot of air moving up, it's almost creating a void down below, right? That's a low pressure area. Where my dry, cold air is sinking, that's pressure, it's pushing down, right? It's a high pressure area. Now, we know that air is going to move from high to low pressure. We already said that, right? So we're going to see that air that has now sunk, start to kind of move back towards the equator. And you get these cells. Okay. Whew, that was a lot. We call those Hadley cells. You're going to see that pop up. All right. Sorry, high-low pressure. I forgot that. Now, we see this on a smaller pattern, even locally, right? If you spend any time at the beach, if you think about during the day, right, the land is going to heat up. That land, warm air, stuff's rising over the land, right? That means a low pressure system. As it rises and it cools, it's going to move out over, say, the water, and it's going to sink back down, right? Which makes that high pressure system kind of come in. So during the day, typically, we're getting again, local wind patterns coming in off of the water, right? Now, if it flips around and you have a really cool night, or cool temperatures, and you have a warmer ocean or warmer body of water, you see the flip-flop happen. So you can kind of get a sea breeze and a land breeze. You may have heard those terms. And again, this is just locally. This isn't on a global scale, okay? All right. Now, if that wasn't enough, we also have to add in the fact that the Earth is spinning, right? So these big cells would be fine, except that we're spinning. So air, we know it's moving back to the equator, but it's also, because the Earth is spinning, moving in a west to east direction, okay? Again, gets a little more complicated. So between 0 and 30, we're moving from an east to west direction because the Earth spins west to east. Now, the winds between the 30 and the 60-degree mark actually are going west to east because the Earth is technically spinning faster at those latitudes. Now, again, we're going to do a lot of work with this in class, so I'm hoping that some of this will help clarify if you're watching this before we do that. Let's just pause there for now. So when you look at the fact that the Coriolis effect is going to impact our global wind patterns, we have to think about this kind of on this level. So if you look, we've got air moving out from 30 to 0 degrees and 60 degrees due to high pressure, right? And it's rising at the equator. It's sinking down at those 30-degree latitudes. From 0 to 30, again, the winds are blowing from east to west. We call those the eastern trade winds, okay? And you can see them kind of all over the case. They're moving east to west, okay? So that's going to drive ocean currents. If you kind of look at the direction here in the north, right, they're going clockwise. In the south, they're going counterclockwise. Now, a lot of people think that means the toilets flush different. It doesn't. It's just the ocean currents. You can flush a toilet in the southern hemisphere, and it's the same as here, okay? Now, we mentioned from the 30 to 60 that the winds are blowing from west to east. We call those westerlies, okay? So this is what's driving a lot of weather patterns in North America, right? If you think about where our weather comes from, it's coming typically across the country over to us. Those are because of those westerlies. And again, we'll get into a little bit more in class about how that works. I've got some good demos for you. Okay. And again, we've got our highs and low pressures. You should have this diagrammed in your notes pretty well to help you out there. All right, so your job with this FRQ you do have to write is I want you to think about how the sun is responsible for just the pattern of circulation that you see at sea. So just that Hadley cell that we see between the equator and the 30-degree south mark. All right, that was a lot. Hope that helped a little bit. Keep learning. We'll talk soon.